So, good evening, everyone. Today is the week 5 discussion of this course, Social Networks, and this course was originally taken by Professor Sudarshan Iyengar, Professor and Head of the Department, Department of Computer Science and Engineering of IIT Ropar, and myself, Ayan Paul. I'm a PMRF Research Scholar from IIT Kharagpur, and I am a PMRF TA for this course. By TA, my responsibilities are I have to discuss few questions that will be very much similar to your assignment, so that whenever you will solve your assignment, you will not feel it's totally new. Okay, so but before that, I always prefer to go through what has been taught in the week so that it can further help us to solve the question. Okay, so let's start the discussion. So today we will be talking about something called as spatial segregation. Okay, so spatial segregation means separation. Okay, and spatial means by region or anything. Okay, spatial means generally it is called region. Okay, but it can be other things also, but spatial, particularly spatial segregation, means with respect to region. Okay, so what does spatial segregation means here? Spatial segregation refers to tendency of individual from different social groups. Okay, the social groups can be example race, ethnicity, religion, income, class, etc. Okay, to become physically clustered into separate neighborhood or regions. Okay, this reason, that is why spatial segregation. Spatial means region, segregation means separation. Okay, so this segregation means separation, spatial means region, rather than being evenly mixed. Okay, so again I am repeating, spatial segregation refers to tendency of individual from different social group. The social group can be anything like race, religion, ethnicity, income, class, anything, to become physically clustered into separate neighbors or region rather than being evenly mixed. Okay, so that is known as spatial segregation. So in social network terms, it means people are likely to have neighbors or connections from their own group rather than from other groups. Okay, so what does this mean? You can see properly in this figure. So how do people occupy houses in a locality? Okay, so this people observation from this experiment, we have people who are from same social group. Okay, this social group can be anything like race, ethnicity, etc. They tend to separate or cluster in a separate group. Okay, so this is one group, this is another 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 group. And the best thing about it, they are separated by reasons. Okay, so we can see this reason is for this green one, G1, this reason is for red one, R1, this reason is for green 2, this reason is for R2, like that. Okay, so they are separated on the basis of different social group with in different reason. Okay, so that is spatial segregation. So you would prefer to stay with the people who are like you. Okay, that is the whole concept, or at least some of them who are like you. Not if even all of them are not like you, but some of them should be like you, then only you will do the spatial segregation. Unhappy people change their house to a happier destination. Okay, so this is totally called as spatial segregation. So we explain this spatial segregation with a model known as Schelling model. Okay, Schelling model. So this Schelling model was given by this Thomas Schelling. Okay, so even when individuals have mild preferences, you can see in this case not all like this is you. Okay, this is you, but here you can see only three people are from your you can say your social group. Others are red, means other five people are not from your social group, but you are staying in that region. Okay, so that means individuals have mild preferences for similar neighbors. Large scale separation can emerge over time. Okay, so even you can see there is mild preference, right? Because five are red. Okay, so this individual has mild preference, but for similar neighbors, large scale separation can emerge over time. So this phenomenon was famously demonstrated by Thomas Schelling through his segregation model. So this model is known as Schelling model or Schelling segregation model. So how it works? Individual occupy location, example house or a house on a grid. Okay, each person prefers a minimum fraction of neighbors to be similar. Not all similar, but minimum fraction. He or she prefers a minimum fraction of neighbors to be similar. If that preference is not met, they relocate. Very easy. If that preference is not met, they relocate to a new region. Over repeated moves, clusters of similar individual form. So this is totally known as Schelling model. So again I am repeating, individual occupy location. This location example house or grid. Each person prefers a minimum fraction of neighbors to be similar. If that preference is not met, they relocate. And fourth, over repeated moves, clusters of similar individual form. So this total is this whole is known as Schelling model. So important insight that we got from here: no individual may want extreme segregation, yet strong segregation can still emerge collectively. Okay, it's like this figure. The individual is not preferring extreme segregation. Not all the houses should be of his same color or of his same social groups. Okay, but still over the time you can see formation of this type of clusters. Okay, so yet strong segregation can still emerge collectively. So this is known as segregation, Schelling segregation model. So what is the decision rule for Schelling segregation model? This is the second. Each person prefers a minimum fraction of neighbor to be similar. So this is the segregation rule. Mathematically, if we see segregation rule or decision rule for segregation. So mathematically, if you want to see for each agent I, number of same type neighbors of I divided by total number of neighbors of I, that should be greater than equal to T. Okay, T is known as tolerance threshold between 0 and 1. Okay, neighbors adjacent cell often 8 in the Moore neighborhood. I will see what is Moore neighborhood. Moore neighborhood is nothing but a grid of 3 cross 3. Okay, 3 cross 3. So if you are in the center, so 3 cross 3, center means you, so 9 minus 1, so 8 neighbors. You will be occupied with 8 neighbors like this. Okay, so let me draw it a bit. How much I can draw? This and this. Okay, so you can see it is a 3 cross 3 grid. 1 2 3, 3 cross 3. Someone is joining. Yeah, so you can see it is a 3 cross 3 grid. Okay, so the 3 cross 3, if you are in the middle, you should have 8 neighbors surrounding. Okay, so that is what has been written. Neighbors adjacent cell. The adjacent cell are known as neighbors, often 8 in Moore neighborhood. This is known as Moore neighborhood. In Moore neighborhood, we have this 8 neighbors. Okay, so if the fraction of similar neighbor is greater than equal to T, okay, you have to first find this. If it is greater than equal to T, the agent is satisfied and he stays at his own place. Agent means nothing but a people. Okay, it can be people from different social group, that is agent. So if the fraction of similar neighbors is greater than equal to T, the agent is satisfied and he will stay there. If the fraction of similar neighbor is lesser than T, in that case the agent is unsatisfied and moves to an empty location. Okay, so this is how your Schelling model works. Okay, so this is the whole thing about spatial segregation and Schelling model. So any doubt in this? You can ask me. This is a very important concept to understand. Any doubt? Okay. So this is the first concept. The second concept that has been discussed is positive negative relationship. Okay, so in a signed network, what is a signed network? Signed network, previously whatever network we are discussing, they were mainly friendship network. So friendship network is always positive. That means if you are connected to your friends, that is a positive relationship. But there can be another network known as signed social network. Every relationship edge between two individuals has a sign. Either it has positive sign or a negative sign. Positive sign means it is friendship, trust, alliance, cooperation. Okay, negative means hostility, rivalry, distrust or conflict. That means it can be enemy. So very easily, if layman terms we can understand. So positive relationship means friendship. A negative relationship means enemy. Okay, positive relationship it is friend, negative relationship it is enemy. Okay, very layman we can understand. Now mathematically how to represent this? This is represented by an adjacent matrix. Okay, Aij plus 1 and minus 1. Okay, if I and j are friends, we call it plus 1, or if I and j are minus, that means we call it minus 1. So this is if we want to understand it by help of matrix, like this relationship, like this is the Morse relationship. Okay, so you are in the center. Okay, and you have to give number to each of this other cell. If this cell is your friend, then you will give plus 1. if this cell is your enemy, you will get -1. So +1 -1 +1 -1 like that. Okay, so that is what has been given here. How we can mathematically express it in the matrix form. Okay, such networks are studied under structural balance theory. Okay, now we have to understand what is structural balance theory. So structural balance theory was introduced by Fritz Heider and later formalized by Frank Harari. Okay, so it studies triad groups of three people and determine whether their relationship are psychologically stable or unstable. Okay, so that is the structural balance theory. I am repeating structural balance theory. It was introduced by Fritz Heider. Okay, that is why it can be also called as Heider theory. Okay, so same thing, Fritz Heider. So that it is known as structural balance theory, and later formalized by Frank Harari. Okay, it studies triads. Triads means a group of three people, and determine whether their relationship are psychologically stable or unstable. Okay, so that is the structural balance theory. Now triads and balance. So how triads can be formed? So there are basically four cases of formation of triads. Okay, so you can see this case, three friendship. Okay, that friendship here, if it is denoted by solid line, that means friendship. If it is denoted by dotted line, that means not friendship, hatred or enemy. Okay, so that is how we have expressed this. So case 1 can be three friendship. A is friend of B, B is friend of C, C is friend of A. All three are friends, so that is why this is case 1. We have case 2. Case 2, if A is friend with B and B is friend with C, but A is not friend with C. Okay, so that is known as this is the case 2. Now case 3, we have only one friendship. B is friend with C and A is enemy with B and A is enemy with C. This is the third case, and we have fourth case where all the three are enemies. Okay, so again I am repeating, either we can have three friends, either we can have two friends and one enemy, either we can have two enemy, one friends, and at last case we can have three enemies. Okay, these are the four cases of triad formation in a signed network. Now consider this three individual A, B, C. A triad has three edges. Okay, a triad is balanced stable if the product of the three edge signs are positive. Okay, like in this case, A, B, C. Okay, A, B, C all are positive because all three are friends. So positive, positive, positive. So if we multiply all three, +1 into +1, that is +1, into +1, that is +1. So this is stable. Now let's move on to case 2. Case 2, we have AB is positive +1, BC is positive +1. So +1 into +1 is +1. But AC is -1. So +1 into -1 is -1. So it is unstable case. Case 2 is unstable. Now what about case 3? Case 3, we have BC positive, that means +1, but here AB is negative and AC is negative. So +1 into -1 is -1, -1 into again -1, that is +1. So this is again stable. And at last we have this case 4, -1, -1, -1. That means -1 into -1 +1, but +1 into -1, that is again -1. So we have case 1 and case 3 as our stable relationship, okay, or balanced triad. This is known as balanced triad. Product of all three S sign, if it is positive, then it is called as balanced triad or stable relationship. If the product is negative, so it is known as unbalanced or unstable triad. Okay, so this case 2 and case 4 is nothing but unstable because product is -1. Okay, so this is how we are mathematically concluding whether it is a balanced triad or whether it is a imbalanced triad. Okay, imbalance or unstable triad. Stable triad, generally we call it stable unstable. So stable triad or unstable triad. Okay, so this is known as structural balance theory. So any doubt in this? Again, an important concept. It is very useful in your question answer. So any doubt in this? Okay, I hope it is clear. Okay, now let's move on to the stable balanced triad. And so again, let me again explain you. Okay, so this you already know, like case 1, all are positive, so positive of 3. So positive of 3 means friends of friends are friends. Okay, stable because no tension exists. Okay, so this is case 1, that is stable, that is this case, this case. Okay, then we have this again stable case, that is case 3. Okay, so this is the case 3, case 2 according here, but case 3, okay, are originally case 3. So case 3, 2 negative and 1 positive. Again, multiply 2 negative is positive, positive into positive is positive. So positive. So it is again stable. So the enemy of enemy is my friend. So you have to understand what is happening here is C is A is enemy with C and B is also enemy with C. So A and B are nothing but friends. Okay, so it is a different thing if we compare this with our previous knowledge of triadic formation. In triadic formation, what happened? Friend of friend is friend. So that means A is, if A and C is plus and B and C is plus, then A and B should be plus. So according to this, you can say that if enemy and if A is enemy with C and B is also enemy with C, then A should be enemy with B according to a triadic closure. But that does not hold here. Here what happens is if if we have this two negative, AC is negative and BC is negative, then enemy of enemy is become my friend. Okay, so stable because hostility constant. So again you can see, just multiply all this, negative negative plus and plus into plus is plus. Okay, so again this is case of stable triad. Now let's move on to unstable triad. So unstable triad, this is our case 1, unstable triad, 2 positive and 1 negative. Okay, so 2 positive, 1 negative. So what will happen is 2 positive, 1 negative. So I don't know where negative negative negative. Okay, so I think, okay, so actually this is case and this is cross. Okay, so let's just, I think I just have do the just reformatted the figures. So just you can see this is this case. Okay, so 2 positive and 1 negative. So 2 positive, 1 negative. So what's happened is A and B are friends, A and B are friends, A and B are friends, and B and C are friends, B and C are friends. So actually here it is just see the diagram. Don't see this. Just see the diagram. A and C are friends and B and C are friends. So A and B. If A and B is your enemy, then what will happen is this is case of unstable relationship, because plus into plus is plus and plus into minus is minus. Okay, so that is why this is case of unstable relationship. Okay, now you will say how this case stabilize. So this, how this case stabilize, this is actually case 2 and this is case 1. Okay, so just this is case 2 and this is case 1. Okay, so how this relationship stabilizes? So very easy. How it is stabilizes is this: either all should be positive, that means A and B becomes friends, or what can say two negatives can exist like this. A and B becomes enemy and A and C becomes enemy. Okay, so that can also happen, or reverse this: A and B is already enemy and B and C becomes enemy and this is friends. Okay, so this is how this case stabilizes. Okay, so AB becomes positive, most natural resolution. So this is the most natural resolution, that B becomes positive. If this is negative, just make this positive, so this can happen. This is how it can stabilize. Or otherwise we have to do this: AC becomes negative or BC becomes negative. By this also we can stabilize this unstable relationship. Okay, so this is one thing. Okay, now there are two negative edges, and if you do this, just multiply this and you can stabilize their relationship. Now what about case 1? Case 1, all are negative. All are negative. If all are negative, how it can turn positive? Just make one positive. Okay, just make one positive. Either make BC positive, BC positive, AC positive, or AB positive. By that you can stabilize it, or make all three positive. Okay, so all three positive is a tough task, so just make one positive and you will get a stable relationship. Okay, so that is how you can stabilize this unstable relationships. Okay, so this is about how you can stabilize a unstable relationship. So any doubt in this slide?
No, sir.
Okay, nice. Okay, so this is the thing about stable, unstable triads. Now let's, yeah, so pattern, friend, friend, result, friend, okay. Enemy, enemy becomes friend, okay. So this you have to remember. Friend, friend, already you know friend by triadic relationship or triadic cluster. Reason, trust spread, enemies enemy become friend because common threat creates a alliance, okay. And friend enemy will always be enemy, okay, because conflict spread. So these are the three cases, okay. Friend, friend will be friend, enemy, enemy will be friend, and friend enemy will be enemy, okay. So these are the three things you have to understand. Now the question is why a friend of friend is a friend. So very easy, why a friend of friend is a friend. We know this triadic closure, AB positive and BC positive, then AC will likely become friends, okay. So triadic closure this. So A, B and BC, okay. A, B, okay, B is common, right? So just write B here. Okay. So just write B here, B, A and C. So B is common, okay. B, A and C. So B, A and C. So B is friend with A and B is friend with C. Then AC will become friend, okay. This is positive, this is positive, this will become positive, okay. So this is known as triadic closure. We have studied again and again, okay. So why friend of friend becomes friend? Because they share a trust through B, because B is the common friend. They interact more frequently. Social pressure pushes consistency, okay. So sociologically, my friend introduced me to their friend, okay. So this is known as a friend of friend will become your friend, okay. And the thing psychologically why it happens, because bonding always increases when you are struggling together, okay. So this is why friend of friend becomes a friend. Now why enemy of enemy becomes a friend, okay. Why enemy of enemy becomes a friend and not enemy? So thing is, if A dislikes B, C dislikes B, then A and C shares a common advisory, like you can see in this diagram, okay. So someone is hating someone is again hating someone, then these two will become friends. Why these two will become friends? Because they share a common adversary, okay. Adversary or struggle, again same case, because if they are struggling together they will become friends, okay. That is why enemy of my enemy will be always friend and not enemy, okay. So hence enemy of my enemy is not is my friend, okay. This produces a stable structure with two negative edges and one positive edge, okay. So mathematically you can explain this. AC, AB is negative and CB is negative, then AC will become a positive relationship, okay. So this is the mathematical thing, okay. Minus minus into plus, if this will be plus then only your structure will be stable. That is why this should be plus. We have two minus, then this should be plus to form it positive. So that is why enemy of my enemy will become friend and not my enemy, okay. So this is the thing about how relationship works for stabilization, okay. So this is the this slide, okay. Now let's move on to the next slide, that is balance theorem, two collation theorem. So what does this suggest is a signed complete graph is structurally balanced if and only if its node can be partitioned into two groups or collision, okay. Two groups or collision, two groups, one can be positive group, one can be negative group, okay. Such that all edges within each groups are positive, all edges between two groups are negative, okay. This is called as two faction structure. Yeah, this is known as two faction structure. So two faction structure also known as two collation, because we have two separate groups, that is why two faction structure or two collation, okay. So how you can explain this or you can watch these things, like if you are fighting between three, if there is a fight between three people, what will always happen is two people will always form a group and one people will be separated, then only the fight can emerge. Otherwise if three are fighting with each other, that will be very unstable, the fight can't be taken place, or we cannot say who will win, okay. So that is why always two people will form a group and the people will be left out. This can also be seen in a four-person chaos. Okay, this is a three-person chaos, like A, B, C are fighting. So what will happen is some two people will form a bond, like A and B will form a bond, or A or C will form a bond, and they will fight with B. That means there will be two groups. So A, C will be group and B is another group. So always fight will be between two groups. Okay, so that is known as two collision theory. If four are also there, then also they will be like this. They will team up, like A and B will team up, and they will try to fight C and D. But again this will be chaos, because again two collision theory is not formed. Then what will happen is C and D will also form a group, and then they can fight. Okay, so this is how two collision theory works. Even you can see this in war between countries. Okay, so war between country, what will happen is two countries are fighting, third country will come and it will it will form a group with the one country. Okay, and that is how like this X country is coming, and it will form a group with country 1 or country 2, and then they will fight another country. Okay, so that is how you can fight, or you can do this collisions. Okay, so this is known as balance theorem or the two collision theorem. So institution behind the theorem: balance means friends clustered together. Okay, so this is balance. That means enemies are across the boundaries. No internal contradiction exists. So these are the three things for balance theorem. To understand balance theorem: friends always clustered together. Enemies are across the boundaries. Enemies are not within the boundary but across the boundary. That means enemy is another group, and no internal contradiction exists. So this is the institution behind the balance theorem. So network naturally split into two groups or two collision. Okay, collision 1 all mutual friends, collision 2 all mutual friends, and mutual hostility between collisions. Okay, so this is the thing about the collision theory, or the two collision theory, also known as balance theorem. Okay, so this is the thing. Now let's move to characterization of a balanced network. A signed graph is balanced if every triangle has an even number of negative edges. Okay, so again I have told you, in we have to generally multiply it. Okay, and multiplication, if multiplication is coming positive, then it is a balanced network, otherwise non-balanced network. So if every triangle, if it has even number of negative edges, then what will happen is negative into negative will form positive. Okay, so positive into positive will be positive. So that is how a sign graph can be balanced, 0 or 2 negative edges. So this should already be understood. Equivalently, the product of edge sign in every circle is positive. That means every circle or every collision, okay, collision or group. Okay, so in every group, product of edge sign must be positive. And equivalently, the graph can be divided into at most two internally friends group. That means only two collision is possible, not more than that. Because more than that, if we will do, again it will, instability will be created. So this is the characterization of a balanced network. So two things you have to understand. One is, in every triangle there should be 0 or 2 negative edges, either 0 or 2. Okay, that is even number of negative edges. Okay, and then equivalently, the product of the signs in each collision, that should be positive. And the graph can be divided into at most two internally friends group. Okay, so this is characterization of a balanced network. Now proof of balance theorem, how we can prove it? That means how we can prove that within this circles, within this two circle, the signs are positive, but between the two circles, when we are connecting the two circles, the edges should be negative. Okay, how we can explain this? So we can explain this: if a completely signed graph has balanced triangles, then it must split into two collisions. So that is the proof of a proof of balance theorem. So what does this means? So our condition should be, if a complete signed graph has all balanced triangle. If all balanced triangle will be there in a completely signed graph, then it must split into two collision. Okay, so let's see one example. How does it we can explain this? So you can see this is the whole network. Okay, this is the whole network. So whole network, we can see this is this is we have this set X. Okay, so this is set X. The upper side this is set X, and the lower side this is set Y. Okay, set Y. So set X node that are friends of A, and set Y nodes that are enemies of A. Okay, so we have, again I am explaining, there are two sets. We have this X group, we have this Y group. So just, yeah, we have this Y group. So Y group is the downward group is the Y group, the upward group is the X group. X group means nodes that are friend with A. Y group means nodes that are enemies of A. Okay, so this is the initial condition. Now what we will show is, in the X group all are positive, means they are friends of A, right? So if we take three nodes of the X group like this, A, B and C, and our condition is all should be balanced triangle. Okay, so balanced triangle, we just know that A is friend with B, okay, and A is friend with C, because upward we have this A is friend, right? So this X group is friends of A. So we can just say that A is friend with B if A is friend with B and A is friend with C. Now we have this balanced triangle, right? Balanced triangle concept means B should be friends with C, then only balance will happen, right? If we say B is enemy of C, then what will happen is plus plus into negative. So plus plus, plus 1 into plus 1 is plus 1 into, if we say BC is negative, then it will be minus 1, then it will not be a stable triangle. So for stable triangle, what we have to do, we have to say the sign of BC should be plus. Okay, then only it is a stable triangle. Okay, so this is the X group. Okay, now let's see about the Y group. In Y group, A is enemy with D, because we know this downward group all are enemy of D. So A is enemy of D and A is enemy of E. Now what can we say about relationship of D and E? Now relationship of D and E, again we have to balance the triangle, right? So relationship of B and E should be positive, then only it should be balanced. Okay, minus into minus is plus, and plus should be multiplied with plus only, then only it should be a stable triangle. So that is why minus into minus is plus, and plus should be multiplied by plus only, then it should be stable. So that is why D is actually friends with E. Okay, so these are the two cases. Now we have to see that if these are in between two group. Okay, so this is X group and Y group. Now we have to prove that there is enmity between the X group and the Y group, then only we can say that our balance theorem is proved. What does balance theorem say is, within the group we have friendship, but across the group we have enmity. So we have to prove that across the group we should have enmity. So how we will prove it? We will take this triangle. Okay, A, B and D triangle. So A, B, D triangle, we know A is friend with B, that is why plus, this is X group. Okay, this link is X group, this link is of Y group, A is enemy with D. Now to make it stable, what we have to do? We have to do a minus sign here. If we will put a plus sign here, what will happen is, it will be if we multiply the all three by putting a plus sign here, it will be negative. That will be unstable relationship. So to make it stable, we have to do a minus sign here. Okay, so if we are doing a minus sign here, that means what is the relationship of B and D? B is this group and D is this group. So B and D, the relationship must be negative. Okay, so that is how we can prove the balance theorem. Okay, so this is the proof of the balance theorem. Okay, so any doubt in this? Any doubt in this? What has been
No, sir.
discussed?
Understood.
Okay, nice. So with this, let's move on to the question answer. Okay, I hope all the doubts are clear. If all the doubts are clear, let's see the question. Let's try to solve the question. I hope you will participate in this session, okay, actively. So let's move on to the question answer session. So we have this topic: spatial segregation, scaling model, structural balance, characterizing the structural balance, balance theorem, forming two collision. Okay. So case study 1: spatial segregation. In the map street neighborhood, two cultural groups, red and blue. Okay, so we have two cultural groups. So these are also called as agent. Any people belonging to red, this is known as agent of red group. Any people belonging to blue, that will be called as agent of blue. Okay, occupy a 3 cross 3 grid of houses. Each family wants a certain number of same culture neighbor. Okay, so that is known as family's threshold, and that is given as 3. It will only stay if at least 3 of its 8 neighbors share its culture. Families with fewer than T similar neighbors relocate to other houses. Over the time, such relocation leads to cluster where like cluster groups together. Okay, so this is the case 1, spatial segregation. So developed by theory that has been required for this one is Schelling model that we have discussed. Agent based modeling. Agent means two group with like we have here red agents and blue agent means two groups. So all the people belonging to red group will be called as red agents. All the individual belonging to the blue group will be called as blue agent. Okay. So in agent based modeling, individual agents occupy position on a grid. Each agent follow a simple local rule. Global patterns emerge from repeated local decision. This is a classic example of emergent behavior. Okay, so threshold tolerance rule. Threshold. This is threshold. So if the neighbors will be below the threshold, the agent will move. If it will be above or equal to the threshold, the agent will stay. Okay. So again, this concept has been discussed. Local versus global outcome. Even mild individual preferences can produce strong collective segregation. We have discussed this role of empty houses. So there are role of empty houses. So this is also important that we have to keep some empty houses. Then only relocation can happen. If we don't have this empty houses, then it is difficult to relocate. Okay, so empty houses enable relocation. They allow the system to evolve dynamically, but empty houses alone do not cause segregation. Okay. Equilibrium convergence, the process continue until most agents satisfy their threshold. The final pattern depends on initial distribution, threshold level, availability of empty spaces. Okay, so let's move on to the question. For threshold t equals to 3, how many same culture neighbors does a family need to remain content? 1, 2, 3 or 4. So any guesses for this? Remain content, how many same culture neighbor does a family need? Any guesses for this?
So 3.
Yeah, 3. Why not 4? 4 is also right?
It is a possibility, but
Yeah. So minimum 3 are
remain.
required, maximum
Yeah,
can be
yeah.
4, 5, 6, anything. Okay. So minimum 3. Okay, so minimum 3, that is the answer. Okay, so yeah, correct answer is 3. A threshold t equals to 3 means the family requires at least 3 neighbors of the same culture. At least. Okay, it can be more than that, but at least you require 3 out of 8 possible surrounding houses to be satisfied. If it is fewer than 3, then they will relocate. So answer 3 is the right answer. Option C is the right answer. Okay. So this is regarding question number 1. Let's move on to the next question. If a threshold will lower from 3 to 1, okay, what is likely to happen to the neighborhood pattern? It will become more mixed, fewer moves. It will become more segregated, more moves. It will remain unchanged. All families will move out. So any guesses for this? If we decrease the threshold, what will happen? If we decrease the threshold, what will happen is it will become more mixed because we are decreasing the threshold. If decreasing the threshold means more and more people will relocate. Okay, so this is the thing. So with a lower threshold, families are satisfied. Less threshold means what will happen is less threshold means people will not relocate. Okay, so t is equal to 1 means we are decreasing the threshold. So families are satisfied as long as at least one neighbor shares their culture. This makes most families content even in mixed neighborhood, leading to few relocation. Okay, so less threshold means fewer relocation and less segregation. Okay, so option A is the correct answer over here. So again I am repeating, if threshold, we are lowering the threshold from 3 to 1. Previously we have seen, previous question there is 3, t equals to 3 is the threshold. Now we are lowering to 1. So what is likely to happen to the neighborhood pattern? So it will become more mixed or fewer moves will be required. Fewer moves are required means fewer relocations. Okay, and less segregation. So this is how we answer this question number 2. Now let's move on to the next question. Question number 3. Which effect is expected when all families increase their threshold from 1 to 3? Now again we are increasing the threshold. First it was 3. Previous question we have decreased to 1. Now again we are increasing. That is 1 to 3. Okay. So fewer relocation, more relocation, no relocation, or no predictable change. So we know this is a reverse question of the third. So last time when we are decreasing the threshold, what will happen is we have fewer relocation. Now we are increasing the threshold, that means we will have more relocation. Okay. So now we will have more relocation. So raising the threshold makes families harder to satisfy. So more of them will find their current relocation location unacceptable and move. This repeated moves tend to amplify the clustering and segregation. So option B is the correct answer. Now let's move on to question number 4. Which of this configuration represents strong segregation given a high threshold? Red and blue home alternate regularly. One contiguous cluster of reds and one of blues. A checkboard of red blue, a random mix of red and blue. Which of this configuration represent a strong segregation? So we have to tell a case where segregation is strong. That means separation is strong. So separation can be strong when we satisfy this case. One cluster will be form of blue and one cluster will be form of red. Okay. So option B is the correct answer. So strong segregation occurs when similar families group together into large homogeneous region. A single red cluster and a single blue cluster best reflect their outcome. Okay. So option B is the correct answer over here. Now let's move on to the question number 5th. Which factors tend to increase the spatial segregation? Higher relocation threshold, more moves needed, more empty houses available to move into, fewer same culture neighbors nearby, family unsatisfied, pre-existing pockets of similar families in the group. Which factor tends to increase spatial segregation? So any guesses for this? Okay, no guesses. So answer will be A, C and D. Okay, higher relocation threshold. If you have a higher relocation threshold, then more moves are required for increasing the segregation. More empty houses available to move into, that is also true. A, B is true. C, fewer same culture neighbors nearby, this is false. And pre-existing pockets of similar families in the grid, so that is also true, because if we have pre pockets, then what will happen is this will increase the chances of segregation. Okay, so A is right, B is definitely right, because more house and to move to, that will increase the segregation. And pre-existing pocket of similar families in the group, that is also true. So C is wrong. Okay, so yeah, sorry. Okay, so more empty houses available to move into. Okay, so that is wrong. Okay, so just see the explanation. More empty houses to move into is incorrect. Okay, so yeah, empty houses is not correct. Empty houses enables movement but do not themselves increase the segregation. Okay, so segregation arises mainly from preferences threshold and initial local structure. Okay, in many simplified models and exam content, empty houses are treated as neutral facilitators, not drivers of segregation. Okay, so this is false. Now what is true? Higher relocation threshold, that is true. More moves required. Okay, more dissatisfaction, more sorting, so this is absolutely right. And B is also right. Act as seeds that grow into larger segregation. So already if we have this pre pockets, then it will increase the segregation. This two are correct. Fewer same culture neighbors nearby. Okay, so fewer same cultures, that will trigger the relocation. Okay, so that is why C is correct. Okay, C is correct, but B is wrong. So according to me, A, B, C, D both are true. Okay, so B is true according to me, but here it has been given that more empty houses does not increase the segregation, but definitely it will increase the chances of segregation. Okay, so according to me, A, B, C, D both are true, but here it has been told B is false. Okay, so A, C and D is right according to this question. Okay, so this is question number 5. Now let's move on to the case study 2, that is Schelling Model. Mason City Council simulates neighborhood integration using the Schelling Model on a 4x4 grid. Houses are colored red or green with some empty lots. Each family has a tolerance threshold T, fraction of neighbors of the same color needed. In each round, any unhappy family below T moves into a random empty lot. According to the simulation, families move towards like colored neighbors over iteration. The number of unlike colored neighbors decreases. The process continues until most of the families meet their threshold. Okay, so again, this is a question of Schelling model. So let's see what are the theories required. Schelling segregation model. This is agent-based model. We have discussed threshold. This is the threshold. We have again discussed. So in the previous, it was only neighborhood threshold. That means if t is greater than 3 or not. But here, in this question, it has been number of same type of neighbors divided by total number of neighbors. Though the meaning will be same because in all the cases, total number of neighbors will be same. Okay, so meaning will be same, but it has been the threshold has been defined in question, not just the count, but it can also be taken like this. That is known as tolerance threshold. Okay, if a house has 8 neighbor, t equals to 0.5, that means you have to multiply 0.5 with 8. That means 4 neighbors should be there. So at least 4 neighbor must be the same type for the agent to become satisfied. Okay, and then we have this role of empty houses enable relocation, make the system dynamic, allow unhappy agents to move. Two empty houses, mobility constraint system may not converge. Okay, so this is another thing. That is why in the last question that can be understood, because too few empty houses, mobility constraints system may not converge. Okay, so this is a thing. Equilibrium convergence, we know most of all agents satisfy their threshold, no further beneficial moves exist. Very high threshold, convergence may be impossible. Okay, if we give the threshold very high, then the convergence may be impossible. If t equals to 0, then it is immediate equilibrium. That means no segregation will be done. Convergence depend on threshold, initial distribution, and number of empty cells. Okay, so again, here number of empty cell is important. So according to me, in the last question, that the empty houses are important. And then emergent segregation. The key theoretical insight: no agent may prefer extreme segregation, yet segregation emerge everywhere. This also we have discussed. Stability condition: if T is too high for a popular mix, full satisfaction may be impossible or may not be possible. Okay, if there are two empty houses, some unhappy agents are trapped. If t equals to 0, no movement needed. So this is the stability condition. Okay, so just remember this will be helpful to you. Now let's move on to the question: why are empty houses included in Schelling simulation? To allow families to relocate into them, to represent unemployed families, to reduce neighborhood density, to buffer interactions between the group. So any guesses for this? Very easy. Empty houses included. Easy, right?
First one.
A, right? To allow families to relocate into them. Okay. So
It is
option,
A.
yeah, option A is the correct answer. So to allow families to relocate into them, empty houses essential because unhappy families need somewhere to move. Without empty lots, relocation and thus dynamic of segregation cannot occur. Okay. So without empty lots, relocation cannot occur. Okay. So this is the concept. That is why we always provide empty houses in the Schelling simulation model. So option A is the correct answer. Now let's move on to the next question. If each house has 8 neighbors and the threshold is t equals to 0.5, how many same color neighbors are needed to be satisfied?
4, sir.
4. Very easy, right? 0.5 into 8. Okay, 0.5 into 8. If it is 0.25, that will be 0.25 into 8, so that will be 2. Okay, so just we have to multiply the threshold with the neighbors. So t equals to 0.5, 50% neighbors, so 0.5 into 8, that will be 4. Okay, so family needs at least 4 similar same color neighbors to be satisfied. So option B is the correct answer. Question number 8. If what happens if t equals to 0? No preference for all the families. No one moves. Everyone is content. Everyone moves at least once. Movement continue indefinitely. Families swap place forever. So any guesses for this? If t equals to 0, already segregation has already
C,
taken
C,
place.
sir.
A is the right answer, right? No movement will take place. If threshold equals to 0, then definitely no movement will take place. Okay, So option A is the correct answer. Okay, so no movement will take place when t equals to 0. Families require 0 same color neighbors to be satisfied. Therefore, all the families are content regardless of the neighbors, and no relocation occurs. So option A is the correct answer. Okay, so again is an easy question. Now, question number 9. According to Schelling findings, which statement are true? Select all. Okay, so means more than one can be true. Okay, select all means more than one can be true. So even moderate neighbor preferences can lead to strong segregation. Many empty houses prevent any relocations. uh, a zero threshold t equals to 0 means no relocation needed. A fully segregated state always occur eventually. So any guesses for this? This is true, right? A zero threshold means no relocation added, okay, needed. Okay, so definitely C is true, right? We have just seen in the previous question. Even moderate neighbor preferences can lead to strong segregation. Okay, so in all the cases we see we have moderate preferences like 0.5 or 0.25 or anything, but still it can lead to segregation. So option A is also right. Many empty houses prevent any relocation. So again, this is you can say many empty houses prevent any relocation. So if there are many empty houses, definitely relocation will happen. But what can happen is if the boundaries is too large, that means so many empty houses in between, so that can prevent some type of relocation. Okay, so that is why this is false. Okay, because we cannot say it will prevent any relocation. Relocation will happen, but it can prevent some relocation, but we cannot say it can prevent all the relocation. So option B is incorrect according to me, and option C is correct. A fully segregated state always occur eventually. Again, this is not correct. Okay, so we cannot say a fully segregated state will always occur. Definitely there can be, if your threshold is too high, it may not also happen. Okay, so that is why option A as well as option C is your correct answer. A as well as C is your correct answer. So yeah, even moderate neighborhood preference can lead to strong segregation. Zero threshold t equals to 0 means no relocation is needed. So these two are correct. Okay, these two are incorrect. So empty houses enable movement but do not prevent it. Okay, so that is why this is false. Full segregation is not guaranteed. The outcome depends on threshold and initial conditions. Okay, so option A as well as option C is your correct answer over here. Now let's move on to the question number 10. Okay, which issues can prevent the simulation from reaching the families satisfied? Too few empty houses available to mix into. That is true. Threshold T is too high for the given mix. Again, this is true. If threshold is too high, then people will never be satisfied, right? So the grid being disconnected. Okay, so no neighbors relationship. So this is not correct because grid is always connected. Zero threshold t equals to 0. If t equals to 0, then what can happen? Then simulation will not happen. Okay, so prevent the simulation from the, but families will already be satisfied. If already satisfied families has been given to you, then families will be satisfied. So we cannot say. Okay, so no simulation will happen here, but we cannot say no simulation is happening because uh, because uh, because uh, because it is unsatisfied, still no simulation is happening. So option A and option B are the correct answer over here. Yeah, two empty houses. Okay, two empty houses and correct answer. This is the correct answer. The too few empty houses available to move into, so that can also prevent the simulation, and threshold t is too high, that can also prevent the simulation. And few houses, unhappy families are nowhere to move, dissatisfaction buzzes. Threshold too high, it may be mathematically impossible for families to reach their required fraction of the same color neighbors. Okay, so why the others are incorrect? Disconnected grid. In standard Schelling model, the grid structure is assumed the grid structure is assumed. Disconnected grid is not a assumed connected. Okay, so grid structure is assumed. That means all the nodes are connected. Okay, all the grids are connected. Okay, grid structure means this type of structure. Okay, so that means all the this type of structure. Okay, this like this. Okay, and this. So this is grid. Okay, grid means we have equal number of column as well as rows. Okay, so 3 into 3 grid. Okay, so in the standard Schelling model, grid structure is assumed. Disconnected grid is not a modeled issue. Does not explain failure to system families. T equals to 0, everyone is satisfied immediately, so convergence is guaranteed. Okay, correct answer, A as well as B. Okay, so these are the correct answer, A as well as B. Now let's move on to case number 3, positive and negative relationship. In a static project team, each pair of the colleagues is marked either friend positive or enemies negative. Found as sign network, a positive edge denotes a friendly alien relationship, while negative edge denotes a conflict or antagonism. For example, Alice Bob positive means friendship, Bob Clara means rivalry. The network can be captured by an adjacency matrix of +1, that is friend, and -1, that is enemy. Now theory is required, positive negative relationship. We have already discussed all these things. Complete graph, this is the complete number of edges in a complete graph. So this formula you have to understand, that is n into n minus 1 by 2, or you can say xc2. Okay, xc2, like x is the number of friends, okay, and c2, xc2, xc2 or nc2. Here if there is n, so this is nc2. Okay, so just, yeah, so this is nc2. So always you have to remember nc2. N is the number of people in the graph. Okay, so if you want to know the number of connected edges, that should be maximum possible connected edges would be nc2. That is nc2 is nothing but this thing, n into n minus 1 by 2. Okay, so this triadic sentiment propagation, we have seen this friend of friend, friend of enemy, enemy, and enemy of enemy is friend. Okay, so this is a thing. Then all this negative, positive, all these things we have seen. And last, negative tie, no tie, negative tie, weak tie. So yeah, negative tie is not equal to no tie. Okay, because this is a sign network, so negative tie, that does not mean no tie. Tie is there, but it is negative. Okay, negative tie is not equal to weak tie, that is also false. It explicitly represent the conflict. Okay, this you should remember. Yeah, so let's move on to the question regarding the sign network. In this sign network, a negative edge between two people indicates they are friends, they are enemies, they have no relationship, it has no meaning. So you know this. This is sign network, negative edge means they are enemies. Okay, so 11B is the correct answer over here. So very easy. B is the correct answer. Negative means enemies or antagonistic, and positive means friend. Okay, so negative edge has been asked, so that means they are enemies. So option B is the correct answer. Yeah, negative sign explicitly represent conflict, rivalry, and antagonism, not friendship or absence of relationship. Okay, so question number 11, option B is the correct answer. Let's move on to the next thing. In a complete graph of 5 people, then suppose there are 2 negative edges. How many positive edges are there? In a complete graph of 5 people, suppose there are 2 negative edges. Okay, so how many positive edges are there? 7, 8, 9 or 10? So any guesses how to do it? Can anyone tell how to do it? If we have 5 people and there are 2 negative edges, then how many positive edges should be there? Okay, so how many total number of edges should be there? That is n into n minus 1 by 2. We have 5 people, so 5 into 5 minus 1 by 2. So 5 into 4 by 2, that means 20 by 2, that is 10. So we have total 10 edges, and out of 10 edges, 2 are negative, so rest 8 will be positive. So 8 is the answer. So again I am telling how to solve the question. So this is how you solve the question. First you have to see, as it is a complete graph, that means all the edges are connected. That means first you have to calculate number of edges. Okay, so number of edges, how you can compute, that is n into n minus 1 by 2. and here it is 5 people, so 5 into 5 minus 1 by 2, so 5 into 4 by 2, that is 10 edges. Out of 10 edges, it has been given to you 2 edges are negative, 2 edges are negative, so 10 minus 2, so we have left 8 positive edges, so 8 is the answer. So option B is the answer. So any doubt in this question, how we have computed? Is it clear?
Yes, sir.
Okay, nice.
Yes, sir.
Now let's move on to the next question. In the adjacency matrix representation, a negative tie is usually denoted by, again, very simple question, negative tie. Negative tie means -1. So option B is the correct answer. Yeah. Positive one means positive friendship, negative one is enemy. Okay. So that is how you denote in the adjacency matrix. What is adjacency matrix? Adjacency matrix means neighbors around you. Okay. So if you are in between, like here you are in between, okay, so here let's say you are 0, then if this is your friend, then you have to put +1. If like here this is your enemies, then you have to put -1. Okay, so that is how you have to build your adjacency matrix. Adjacency means person that are adjacent to you. Okay, you have to give a sign to it, sign or number to it. Okay, so that number is +1 if it is a friend, that number is -1 if it is a enemy. So very easy. Now let's move on to the next question. If A, B is positive, that means friendship that means A and B is connected with a positive edge, B and C is connected with a negative edge. What is implied over the sentiment of A and C? Okay, via B. Okay, so that means, let me draw the triangle A, B, C. Okay,
Positive, sir.
A, B, C. Okay, positive. A, B is positive, B, C is negative. Then what should be the sentiment of A and C? So very easy. How you can understand the sentiment of A and C? You have to make the triad stable. So how you can make the triad stable? You can make the triad stable if your sign is overall multiplication of sign should be positive. Okay. So if we put minus here, so what will happen? Minus into minus into plus. That means minus into minus is plus, and plus into plus is plus. So it should be positive. Sorry, negative. Okay, it should be negative. So option B is the correct answer. Negative. Okay, because negative into negative will be positive. Positive into positive will be positive. If we put positive here, so positive into negative, negative, negative into positive, again negative. Okay, so we have to do a balanced relationship. So that is why AC will be negative. So option B is the correct answer. Okay, option B is the correct answer. So balance theory, we have structural balance theory. We have used the structural balance theory. Otherwise, you can also friend's enemy is my enemy. Okay, that type of introduction, from that type of introduction also you can solve it. Better just to use the balance theory. It is structural balance theory. It is very easy. Okay. So this is the thing. Which of the following describe negative edges? They indicate enmity or antagonism. They are represented as -1. They indicate a strong friendship. They indicate a neutral weak tie. So again, very easy. Negative edge means they indicate enmity. That is true. They are represented
A
by
and B,
-1.
sir.
So A and B are the correct answer. C and D are false. Okay. So yeah, A and B are the correct answer. So let's move on to case number 4. That is the fourth case. A small team. This is structural balance case. A small team of 4 engineers has fully defined a pairwise relationship. Each marked plus friend minus enemy. Structural balance theory says a triangle of 3 people is unstable. You know all these things. Okay, this is positives. Okay, positive ties. This is tie. Okay, just I think it has not come. This is ties. Okay. One positive tie, in other word, a balanced triangle. There are either 0 or 2 negative edges. This you have studied. For example, Alice Bob Carroll with positive edges is balanced, and Alice Bob Carroll are friends positive. Okay, so all these things you know. Just move on to the question. These things you have just explained and you know everything. Let's move on to the question. Okay, which of these triangles as sign are balanced? Positive, 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 negative, positive, negative, 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 negative. So
A,
you tell me
C.
what should be balanced?
A and C, sir.
A and C. Yeah, A and C are the correct answer. Okay, so positive, positive, positive will be positive. Positive into negative, negative. Negative, negative will be positive. Positive into positive will be positive. So A and C are right. B is not right. Positive, positive into negative will be negative. Negative negative into negative will be negative. Okay, so A and C is your correct answer. Okay, so A and C is your correct answer over here. Yeah, A and C is your correct answer. Now let's move on to the next question. In a balanced triangle, the number of negative edges can be 0 or 2, 1, only 0 or only 3. This also you know it should be 0 or 2. If it is 0, yeah, if it is 0 only positive, 2 negative negative, so that will be positive. So option A is the correct answer. So option A is the correct answer. Let's move on to the next question. Which global outcome reflect a structurally balanced network? Select all. That means more than one is correct. Okay. Select all means more than one is correct. All individuals are mutual friend. Positive between all. The group splits into exactly two fractions with only inter-group hostility. Okay. Every triangle in the group has two positive edges. Everyone is mutual enemies. So any guesses for this? All individuals are mutual friends. That is true, right? Very true. The group splits into exactly two fractions with only inter-group hostility. We know if it is a structure balanced network, then two collision theorem will be applied. In two collision theorem, what will happen is the groups, the total number of people, they split into two groups or two collision. Okay, with inter-group hostility means inter-group enmity. The inter-group will be enemy. Okay, inside the group that will be a total sign will be positive. Inside the two group, like if we have A group and if we have B group, in A group if we multiply all the sign that will be positive, and B group if we multiply all the sign that will be positive, but any relation between A group and B group that will be negative. Okay, so that is why option B is correct. Every triangle in the network has two positive edges. Every triangle in the two positive edges, that is false, because two positive edges then means one, there will be one negative edge, so that will be structurally imbalance. This is false. Everyone is mutual enemies of all, this is also false. Negative 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 will be negative negative, we have to add a positive here to form it structurally balanced. Okay, everyone is enemies, then it won't be a stable group. Okay, so that is why option A is correct and option B is correct. Option A as well as option B is correct. Okay, all individuals are mutual friends, that is correct. The group split into two fraction with intergroup hostility. Okay, two hostile fraction with friendship inside each fraction ensure every triangle has 0 or 2 negative edges. Okay, so that is how the explanation has been given to you. So option A as well as option B is the correct answer. Let's move on to the question number 19. If a triangle has all three relationship, negative, AB negative, BC negative, AC negative, structural balance theory predicts two of them will become friends, one negative will change to positive. Okay, if our triangle has relationship negative, all are negative. Okay, so what will happen to make it balanced? Two of them will become friends, one negative will change to positive. Okay, so that is true. If one negative will change to positive, then negative negative will be positive, positive into positive will be positive. So option A is true. All three remains enemies indefinitely. Definitely this is false. If all are three will be enemies, then what will happen? Negative negative negative, again negative, so this is false. All three will become friends. Okay, so all three will become friends. So yeah, that can be true, though it is a difficult case. But if all three will become friends, then again a happy case or stable case. This situation is already stable. No, this situation is unstable. So option A as well as option C is your correct answer. Okay, C is not correct. All three will become friends. Has three relations, the structural theory predicts. Has three relation and a structural balance theory. So all three will become friends. This will be structurally, this will be balanced, right? So two of them will become okay. That is true. So this is true, definitely a triangle with three, yeah. But option C is also true. Okay, so option C is also true according to me. Okay, so option C we will get a positive. So option C is also true. Okay.
I think the question was wrong, sir.
Yeah, yeah. Can you repeat?
I think the question was wrong, sir.
Question is wrong. If a triangle has three relationships negative, structural balance theory
Oh,
predicts.
sorry, I meant the answers.
What? Can you please repeat?
I meant the answers were wrong, sir.
Answers are wrong. Yeah, answer A is right. Two of them will become friends. Definitely, that will be true. To make it structurally balanced, and if all three becomes positive, that means all three becomes friends. That will also make it structurally balanced. So A as well as C should be correct answer. Okay, not A but A as well as C. Okay, so this is the correct answer. A as well as C. Now, which of the following triangles are unbalanced? Plus plus plus, that is positive. Balance, plus plus minus, again positive. This is negative. Okay, this is unbalanced. Option B is
So B
unbalanced,
and
positive.
C, I mean B
Uh,
and D.
yeah, D is true and
B and
positive.
D.
Yeah. So option A and C are false. Okay, are unbalanced here. Unbalanced has been asked. So unbalanced. This is unbalanced and this is unbalanced. Okay, so option B as well as option D is the correct answer. Yeah, option B as well as option D. Okay, so you can just see here 0 means yes, 2 means yes. If even number of negative edges, that means balance. Okay, if odd number of negative edges, that means unbalanced. So this way also you can remember it. Okay, if it is even number of negative edges, balance. Odd number of negative edges, imbalance. Okay, so that is how you can. Okay, someone is joining. Yeah. So let's move on to case study 5, historians model international relationship among 5 countries as a complete signed graph. Harari's balance theorem says a balance complete network must have one of the two global structure. Either everyone is a mutual friend, all positive edges, or the countries partition into two hostile camps. In the two camp case, each within each camp is positive and every tie in between camps is negative. For example, Europe could split into two blocks with friendly alliances inside and enmity across. Okay, so this is a case of balance theorem or two collision theorem. Okay, now all this theory I have already discussed. Okay, at the triad level, you know how it can be balanced: zero negative edges or two negative edges. All edges within the group are positive, all edges between the group should be negative. Okay, so this too you know. Single friendly block, all these things you know. I'm not discussing it. Edge counting in balance. Okay, if balance network is split into groups of size A and B, then it should be positive edges AC2 plus BC2. Okay, so that is how we can calculate the positive edges, because in as there are two teams and in between teams we know always positive edges will happen. So AC2 plus BC2. Okay, so that by that you can calculate the positive number of edges. Necessary and sufficient condition: if triangle is balanced, network has two collision structure. If network has two collision structure, triangle is balanced. So this reverse is true. Okay, so this is the thing. And other things already everything has been discussed. No triangle have exactly one negative side. Triangle can have three negative side. Okay, so that also you know. Negative that odd number of negative edges should not be there. Okay, so this all these things you know. According to balance theorem, a balanced complete graph can have how many antagonistic blocks? Okay, one, two.
One, sir.
How many antagonistic blocks? Two, right? A balanced complete can have at most how many antagonistic block? So at most it can have two antagonistic blocks. Okay, so it should be, yeah, two. So what can happen is like this and this. Okay, so what can happen, all this are negative over this block. Okay, but total when we multiply it, that should be even number. Okay, then only the total will be positive. Okay, and then we can have this block all negative. Okay, so this also it can have plus, but in between the relationship, if we do a relationship in between, that should be positive only. Okay, sorry, negative only. Just, yeah, in between that should be negative relationship only. Negative, negative, negative. Okay, so this is how it can happen. Okay, all here negative, all here negative. as this is one collision, that is collision A, this is one collision, that is collision B, all negative here, all negative here, and in between the relationship is negative. Okay, so that can be happen. So one block, everyone is mutual friend, exactly two hostile blocks with friendship inside and enmity across. More than two antagonistic blocks is impossible in a balanced complete graph. Okay, so this is the thing. Option B is the correct answer. If a network of 5 countries is balanced and not all edges are positive, what must be true? It splits into exactly two hostile collision. All edges are negative. Some cycle of 3 countries has two positive edges. The network must be disconnected. If a network has of 5 countries is balanced, not all edges are positive, what must be true? Okay, it splits into exactly two hostile collision, because we have already told the 5 countries are balanced. If it is a balance, then it will definitely split into two hostile collisions. Okay, so option A is the correct answer. Yeah, if the network is balanced and all not all edges are positive, the theorem guarantees a two-camp structure. All other options contradict balance theory. Okay. Which condition hold in any balanced complete network? No triangle exactly has two positive ties. The node can be partitioned into two groups. Which condition holds in balanced? That means which is true. Okay, no triangle has exactly two positive ties. Okay, that is true. If two positive tie
D is correct, sir.
B, okay, the nodes can be
No,
partitioned
sir, D. All negative edges are between
between the two
the
groups.
two
Yeah,
groups.
this is correct, but we have to select all. That means we have to select more than one. Okay, so no triangle has exactly two positive ties. So that no pos has exactly two positive tie, it has two positive tie, then one would be negative tie. Okay, so that is not correct. Positive negative will be positive negative will be negative. Okay, so no triangle has exactly two positive tie, that is true. Okay, either it will have three positive or one positive. Okay, that is why this option A is correct. Option D is correct, that is true. And what about B and C? The nodes can be partitioned into two groups. Okay, so yeah, if balance has happened, then this is true. Every edge in the graph is positive, that we cannot say. Okay, so A, B as well as D is the correct answer. Okay, A, B as well as D is the correct answer. Okay, every edge in the graph is positive, that we cannot say. Okay, so not that is not required. So that is why option A, B as well as D is the correct answer. Okay, triangle with two positive edges, one negative edges, disbalance, negative ties only occurs across groups. So that is why option D is correct. And what about B? The balanced network admits a two group partition theory. So option A, B as well as D is true. So A, B as well as D is true. Now, which scenarios indicate the network is not balanced? A triangle with two positive and one negative edge, all edges in the network are positive. A triangle with zero positives, all three negatives. Nodes are separable into two groups with only
A
one.
and C are correct, sir.
Okay, a triangle with two positive and one negative edges, that means yeah, structurally not balanced. A triangle with zero positive, yeah, this is true. All edges network in the network positive, that is balanced. Nodes are separable into two groups, that is again balanced. So A as well as C is the correct answer. Yeah, absolutely. A as well as C is the correct answer. Now let's move on to question number 25. This is the last question of this case, and we have another case coming up. In a balanced network of 5 nodes split into groups 2 and 3, how many positive edges exist? 4, 5, 6, and 7. So that is 2C2 plus 3C2, right? So 2C2 plus 3C2, that will be nothing but 2C2, that means 1, and 3C2, that is 3 into 2 by 2, that is 3. So 5 will be answer. 2 plus 3, that is 5 should be the answer according to me. No, yeah, 2C2 is 3C2 is 3. Okay, sorry, 2C2 is 1. Okay, so sorry, very sorry. So 2C2 is nothing but 1. Okay, not 2. Very sorry. So 2C2 plus 3C2, that is 2C2 is 1 and 3C2 is 3. So 1 plus 3, that is 4. So 4 positive edges will be there. Okay, just we have seen in the theory. This is the theory. Let me show you again. This is AC2 plus BC2. Okay, so AC2, that means A into A minus 1 by 2, and BC2 means B into B minus 1 by 2. Okay, there it is 2C2 plus 3C2. So 2 into 2 minus 1 divided by 2, that means 2 into 1 by 2, that means 1. And here 3 into 2 by 2, that means 3 into 2 by 2, 2 cancel, so 3. So 1 plus 3, that will be equal to 4. So 4 will be the correct answer. Yeah, 4 will be the correct answer. Option A is the correct answer. Now let's move on to the last case, case number 6. A company must form two project teams from 7 employees. Each pair of employees is a signed relation, plus for collaboration, negative for conflict. The goal is to split them into two coalitions so that friends are grouped together and enemies are separated. In an optimal split, all positive edges lies within the group, all negative edges lies between the group, minimizing the internal conflict. Again, all the same two coalition theory we have seen again and again, nothing to see here. Let's move on to the questions. Okay, anything that has been needed here? Signed connection to maximum cut. Okay, so what is this? If we focus on the separating negative ties, splitting nodes to maximize negative edges across the partition is equal to maximum cut portion. Maximum cut partition nodes in two groups to maximize number of crossing edges. This problem is NP hard in general. Okay, so this is a new thing, greedy heuristic. Since optimal partitioning is computationally hard, practical approaches use heuristic. Okay, start with random partition, move individual if it improves the objective, stop when no local improvement occurs. Okay, so this is a heuristic, greedy heuristic. That means we perform the greedy approach. First we move two groups into random position, and then we keep on changing one nodes one by one. If our objective function is improving, or we are going towards the objective function, then we will move again and again to the same pattern. If our objective function is not improving, then we will stop. So this is greedy method. Local balance plus versus global partition. Triadic balance, you know, two fraction. Global structure, you know, two collision, that means true collision. Okay, optimization formula. Okay, so there is some optimization formula. By that also you can do in triangle, plus plus minus, A and C must be separated. This preserve the balance. So again, this is that nothing but your structural balance. So in an ideal two collision split, which condition holds? All ties within each teams are positive and across teams are negative. That is true. No ties are cut by partition. Exactly half the positive ties must cross between teams. Each team has equal size. So option A is the correct answer. Very right. Option A is the correct answer. All ties within teams are positive and across are negative. So option A is the correct answer. So this is the definition of ideal two balance partition. This you know. Let's move on to the next question. Which strategies exemplifies a greedy heuristic for forming the collision? Start with a random division, then iteratively move individuals if it increases satisfied ties. Group alphabetically by name. This is false, definitely. Put all friends in one team and ignore conflicts.
First one is true, sir.
First one is definitely true. Put all friends in one team and ignore the conflicts. Okay, so that can also be done. So C is also true according to which example. Yeah, so here it has been told greedy heuristic. So you have to go with first one only. Okay, random, start with a random division, then iteratively move individual if it increases satisfied ties. So this you have to do. This is not true because here specifically it has been asked greedy heuristic. Okay, so that is why option C is not right according to for this question. From one team as all positive and other as all negative. This also we don't do in greedy heuristic. Greedy heuristic, what we do, start with the random division, then iteratively move individual if it increase the satisfied tie. That is what we do. So option A is the correct answer. So let's move on to question number 28. Okay, splitting nodes to maximize separation of negative ties is equivalent to which classical problem? Splitting nodes to maximize separation of negative ties. Maximum cut on the negative edge subgraph, minimum spanning tree, click cover, and Hamilton cycle. So this is the correct answer, maximum cut on the negative edge subgraph. Okay, this is called. So yeah, placing endpoints of negative edges on opposite sides maximizes the number of cut negative edges. Okay, so again, placing endpoints of negative edges on the opposite sides maximize the number of cut negative edges. Exactly, max cut problem restricts the negative tie. So this is known as max cut problem. You just have to remember for this question. Okay, so this method is known as max cut problem, and option A is the correct answer. Let's not just discuss this question number 28. You can just search over it. Okay, so in triangle with AB positive, BC positive, AC negative, which groupings form balanced teams? AB and C, AB and C, yeah, AB and C. Okay, ABC, BCA, ACB, ABC together. If ABC together, yeah, ABC together does not make, because ABC, we just do the ABC positive positive into negative, that will be negative. So definitely it is not D. Okay, what about AB and C? AB and C. So let me just draw it. Okay,
I think all of them are correct, sir.
all together correct. ABC all together. That is wrong, right? ABC, ABC,
Except
ABC.
D.
Okay, so let me move, draw this. AB positive. Okay, BC positive, and AC negative. Okay, so AB and C, AB and C. Okay, that is true. AB and C is correct. That is true. And what about BC and A? BC and A, BC positive and A, BC positive and A, BC positive and A. These are all two are positive, and yeah, this is also correct. BC positive and A. Okay, so A, but the tie between BC and A, that is positive and negative. So this can't be true. Okay, this is BC and A, right? So one is positive, one is negative. So that does not make sense, right? That should be negative. Okay, so AB and C is correct. AB and C, ABC, AB and C. Okay, AB and C, AB is positive and C negative. Okay, so this is one. So this is also, we can say, AC and B. AC and B. What about AC and B? AC and B. Uh, AC and B. AC and B. AC is negative. Okay, AC is negative and it is forming positive. So this is correct. Which group forming balanced team? So AC and B should forming balance. AC negative and B. AC negative and B. So all the positive. So according to me, C is the correct answer. All three are false. This is false. This is false. This is false. Triangular which grouping form balanced teams? So balanced team, according to me, AC and B is correct. So C is correct. Okay, C is the correct answer. Other are false. Let's see the question. A and B is written. A and B is written. C should be the correct answer over here. Okay, so why AC negative tie AC? So AC must be separated. AC and must be separated. AC must be separated. But here, if we go with A, B and C, A, B forming one group and we have C another group. But here, there is a positive relation, there is a negative relation. So this is false according to me. B, C and A, B, C and A, if we go there, just, yeah, just if we, B, C and A. Now B, C and A, what happening is B, C and A. B, C and A, again these two are the team, but here we have positive here, we have negative here. Again, this is contradiction. Now AC and B, that is true. Now let me show you why that is true. AC and B, right? So AC and B, AC, this is negative and B is positive. Okay, so what will happen is this is negative but this is positive. Okay, so that is why this is true. And ABC together, ABC together, we know positive positive into negative, that will be negative. Okay, so that is why this should be false. So D is definitely false, and according to me this C should be right. Or they are talking about, or what I think they are talking about, they are talking about this. Okay, so what they are talking about is they should have negative relationship between the two. Okay, So if we do go from here A, B and C, okay, A, B and C, A, B and C, A, B, this one and C, this one. So yeah, negative relationship, but this side only we have negative relationship, right? A, B is negative, B, C is, this side only we have negative, but this side we have positive, so cannot say. And AC, B, AC, B, AC, B, AC, B, AC, that is negative, positive, positive. Okay, so that is why positive relationship they have
Sir,
told. Okay, so
I think
let me
it's
explain.
like,
Yeah,
no,
let me explain you how they have written it. So A, B, and C. What A, B, and C? What is happening? This is a team and this is a team, and in between them we should have one negative relationship according to them. Okay, so if we do not connect this edge, okay, sorry, if we connect this and this edge, okay, and if we do not connect B and C, what will happen is this is a team and this is a team, okay. So this is a team and C is a team, okay. A, B is a team and C is a team, and we have one negative relationship. That is why it is true, okay. So that is why it is true according to them, okay. This is true according to them, okay. And again this case, if we connect this two and we have this, then what will happen is BC, we have positive relationship, and BC we have connect positive relationship, and if we connect C to A we have negative relationship. So that is why this is correct, okay, BC and A. So that is why this is correct, okay. And this is not correct because AC, if you are connecting, that is negative relationship, we have positive relationship with B, okay. So that is why this is false. So that is why A, B as well as A, B is the correct answer. Okay, D is also false. D is definitely false. There is no question about D. D is definitely false. And A, C is correct because they are getting on one negative relationship between A, B and C and B, C and A. Okay, but here we are getting one positive relationship. That is why this is false. Okay, so we know according to two collision theory we should have negative relationship between two teams. Okay, so that is why we are getting negative here and we are getting negative here. Okay, so that is why this option A as well as option B is the correct answer. But D is definitely wrong, there is no question, and this is wrong because we have positive relationship, that is between BC we have positive relationship. That is why this is false. Okay, here we have ABC, but we have negative relationship between A and C. So that is why this is true. Okay, BCA we have negative relationship between A and C. Okay, so this is true. So option A as well as option B is the correct answer. C is false because A, C, B we have one relationship and that is positive between B and C. So that is why this is wrong, and A, B, C together, that is definitely wrong. So A as well as B is the correct answer. Okay, so you understood this?
yes, sir.
Yeah, everyone understood, right? This? Okay, so let me move to the next question. That is the last question. Which of the following describe characteristics of an optimal two team partition? Positive ties maximized with each team. Internal negative ties are minimized. All negative ties end up within teams. Negative ties lies between two teams. So this is correct, definitely. Okay,
Sir,
option D is
option D.
all negative ties end up within all negative ties end up within teams. uh, that we cannot say, so this we cannot say. It can be true, it cannot be true. Okay, so that we cannot say. Internal negative ties are minimized, so that we can say, or internal negative ties are minimized. So we can say, we cannot say, because total number, total multiplication should give you positive. Okay, so internal ties, if it is minimized, so definitely can help you. Okay, positive ties are maximized with each team. Again, this can help you. Okay, so option A and B can help you. Characters of an optimal team partition, this can help you, but this should not be always true according to me. So always true should be D. A and B is partly true. Okay, so A, B as well as D. Yeah, A, B as well as D. So definitely D is true. Okay, now these two are partly true. Okay, so optimal encourages collaboration inside the team, pushes. Yeah, so this thing, this A and B, we can say, yeah, it is partly true, but we cannot say it is completely true. But option D is the correct answer overall. Okay, so option D is the correct answer. So any doubt in this?
No, sir.
Okay. So with this we have ended the question answer session, and now just show you some of the codes that will be interesting. Yeah, so this is a two collision. Yeah, so this is Schelling model that I should show you. So just change the runtime to TPU, that is good, and let's run it. Yeah, so your code has been run. Now you can just change this. Okay, change this, like let's me put it 0.25, that is threshold. That means you know what is threshold is. Okay, so threshold I have also defined here. Threshold, yeah. Threshold tolerance level, minimum percentage of neighbors of an agent required to be same type to stay their current location. Okay, so this is the thing. So I have just changed the threshold to 0.5. I have density here is density here is percentage of grid occupied by the agent. Okay, so that is total agent grid size square into density. Okay, so this just changing the density, like just changing it to 0.3. Okay, and minority, what is minority? Minority is nothing but the ratio, the balance between the two group. Okay, example 0.5 is an equal split. Okay, that is the ratio. So let me change it to 0.3. Okay, and let reset the grid. Okay, so you can see now the grid has been reset. Okay, so density we have just decreased the density. That means we have decreased the number of blank spaces. Okay, so blank space we have increased. Okay, density decrease means we have increased the number of blank spaces, and we have decreased the the red and blue nodes. Okay, so that we have done. Threshold, we have decreased the threshold. That means now your simulation will happen quickly. Okay, or segregation will happen quickly. Minority is percentage of blue and red. Okay, so 0.3 means blue is 0.3 and red is 0.7, like that. Okay, so let's run simulation in one step. Okay, so single step we have seen this. Now you can see this is the similarity ratio. Previously it was 0.6, but now the similarity has been increased to like 0.7. Okay, that is in one step. Now run the full simulation. You can see when I have just run the full simulation, this is how it has taken place. Okay, so run the full simulation. What's happened is the your similarity measure increases to your point 0.9 approx. Okay, in 5 iteration. Okay, so this is how you can do it. You can also again reset the grid, like threshold, let me increase to 0.4. Okay, let me increase to 0.4. Right now it will take more time. Density, let's keep density as it is, and minority or as it is. Now let me run the simulation. Now it will take more time. Okay, okay, 0.4, 0.3, reset the grid. Yeah, 0.4 threshold, density this 0.3, and this is minority. Okay, run the full simulation. Yeah, now you can say now this is the threshold 40%, and now this is yeah, five, up to 5 it has been shown, but now it will take, the global simulation will take more time. Okay, so that is how you can check it. So this is the scaling segregation model. You can play with this code. Okay, you can just copy this code to your drive, you can change the parameter, and you can see the results. Okay, so this is one code. Similarly, I have also given a code regarding this Hader balance theory. Okay, so this code also you can check it. This code is very similar, like one that has been shown to you in your class. Okay, so this you can also check it. Okay, like this code, what does it gives? It gives this is the initial network stage. Okay, so here you have this collision 1 2 4 5 6 7 6 8 10. So this is collision 1, and this is collision 2, 9 3 and 7. Okay, Now after final step, this is your collision. Okay, so yeah, initial unstable triangle 64 network stabilized. After step 7 your network stabilized and it has formed two collision. Okay, so one collision is this shown by this. Okay, 739 initial. Yeah, this is the initial network. Okay, so initial there is no collision. Okay, so all edges are in the same color, all nodes are in the same color, gray color. Okay, now after this formation of this two collision theory, what happens is we have this two collision 9 3 and 7, 9 3 7 in one color, so this is one collision, and we have second collision or second group in this sky blue color 4 5 10 2 6 8 and 1. This is another collision. So this is how we perform the headless balance theory. Again, you can just copy the code to your drive and run the code and you can see the results. Okay, so this is another code. Okay, so this are the two codes that has been given to you for this week. Okay, so this is the thing. With this I am ending the session for today, and we will meet not on the next Tuesday. Next Tuesday I have some conference, so that is why next Tuesday I will not be available. I will try to prepone your class and take it on this Friday or Saturday. Okay, you will be intimated, and next to next class we will be on the same time, that is Tuesday 6 to 8 p.m. Only the next class will be preponed or preponed. Okay, either on Friday or either on this Friday or this Saturday. Okay, so by this I am ending the session for today. We will meet on this Friday or Saturday.
Thank you,
Okay,
sir.
okay.
Thank you, sir.